Hi, so in this screencast, I'm following up about this analysis of the number of splits in terms of what is the best accuracy. Last screencast, we saw that using either 1, 2, 4, 10, or 20 splits, they all give about a test accuracy of 92.1 to 5%. And don't get confused here, it says val accuracy, but that's just the default column name from keras when we use this validation data kind of argument to the fit function. But actually, this is the accuracy with respect to the test set, because here we specified validation data equals list x test map y test, where these test data sets are data sets that have been held out and have not been used at all in model training. So, this is kind of suggestive. We've got a few numbers for one train test split, but what if we wanted to do this whole thing for a bunch of different train test splits? So that would give us more information about whether this, one approach or which number of splits is consistently better across lots of different train test splits. So let's code that up so we can see if there is a consistent difference. So going back up in our code, we were working on this refactoring of the split computation. So here what I did is I have a for loop over split I from 1 to max splits. And this one is going to be, it's going to be doing the different, it's going to be doing 20 different splits because I specified max splits equals 20. For each one, it's going to be training the model on the train. It's going to be doing a validation split of the train set into 70% train or subtrain and 30% validation. Then it's going to be saving these train and validation metrics to this split metrics list of data tables that we're going to analyze later to do our analysis of which parameters to choose. So I mean that. So here now we have split I and max splits. So if we look down, before we had this n splits thing. So we're gonna have to get rid of that because that's not a variable that we're using anymore. And what we can do is, to make this faster, is we can do some parallelization. First, let me pop up my system monitor. Is that right? Maybe just monitor, resource monitor, right? That's what they call it in Windows. So in CPU, in this system, I have 12 CPUs, it looks like. CPU 0 to CPU 11. And then we have a total CPU utilization up here. As you can see, like right now, most of the CPUs are not really doing anything. Maybe one of them is running some background processes. But if I run this for loop, let's do that right now. What's going to happen is it's going to do all of this computation sequentially. So we see that there's a little spike and it starts to go up. But not all of the processors are being used because it's just doing this computation sequentially. So that's not going to be very slow. So what we can do though is we can truly parallelize this thing. So let's try to do that. Going to our for loop, what we're going to do is we're going to use, instead of a for loop, we're going to use this this function called future.apply, future.apply. And so what that's going to do is, basically to convert our for loop code to our future code, basically all we have to do is, here we put as the first argument to that future.apply function whatever we had on the right hand side of in the for loop. And then we're going to give it a function that's going to be executed in parallel. So here, function split I is going to be a function that's called for each split I parameter from 1 to 20. And so that's the first thing. The second thing is, here at the end, you know, instead of having this split metrics list being written to, what we're going to do is we're just going to return that whatever corresponding data table that we would have written to that list element. And so what's going to happen is that thing is going to be returned at the end of that function call. That's what happens in R if the last thing that is evaluated in the function is returned. And then the result of that whole thing is going to be stored in the split metrics list, which is going to be a list of all of these items, but they're going to be executed in parallel. Well, depending on what kind of feature backend you have. So in R, we have this package called feature that can let you specify the backend for doing the parallel computation. So here I'm going to say future plan. They called it plan. So if you do future plan multi-process, you know what that's going to do is it's going to parallelize over all of the using a separate R process. So if we execute this code now, let's take a look at the CPU resource utilization. So you can see now that this green CPU utilization went up really quickly, right? So it looks like now we're using a lot more of our CPU power than we were before. And here it looks like it's going up to 100% actually. Maybe this first period was like spinning up a few more like Python processes or something. But anyway, so what is happening now is it's running all of these 20 things in parallel. Well, and you can see now all of the 11 or 12 CPUs on my machine are being maxed out. So the computation should be going 12 times faster than it was before. So after that, what are we going to do, right? We're going to get split metrics list. And it's going to be a list of 20 different results from the 20 different splits that we did. And wow, look at that. It's already done. Wow, that was a lot faster than in the previous tutorial. Huh? So let's see if this works. Let's do split metrics. And so again, yeah, so this is the list for all the epochs between 1 and 100 and all the splits from 1 to 20. What are the different loss and accuracy values for the training and the validation set? So similar to the computation we did last time, but a lot faster because we did that in parallel using the different CPUs on our computer. So after that, you know, to do a similar kind of analysis to what we did last time, we need to have a, you know, we need to kind of process these data in order to get what are, you know, to get these mean validation curves, right? So here, here, the split means that we're computing here, what it's doing is for every value of n splits and epoch, you know, compute the mean of all of the corresponding loss values. So, you know, that's not going to work anymore because remember we got rid of that n splits variable. So instead, what we can do, we can try to do is kind of, we can try to do a for loop. So how about, let's call this split means list. Initialize that as an empty list. And then let's do for n splits in 1, 2, remember the values we used last time were 1, 2, 4, 10, and 20. But now we've done all these computations, so let's just do all of the values between 1 and 20, just so we can see what that looks like. And so what we're going to do in each one of those cases, well, what we're going to do is we're going to take split metrics, and we're just going to take all of the data for which split I is less than or equal to n splits. All right, so that's going to give us some subset of these data on which we're going to compute a mean validation curve. So for that guy, what we're going to do is we're just going to do the same computation that we specified in here. Compute the mean and the SD of the validation loss. Do that over, sorry, we need to get rid of that square brackets. Do that for all the different values of epoch, now just one variable. And now let's save the result in split means list and splits. I think, sorry, we need to edit those square brackets again. And I think here we need to add a variable for n splits so we can have that information when we do our analysis later. So let's see what that looks like. First of all, that should be really fast because we're just doing a summarization of all of that data that we've already computed. So here, let's compute split means now as do call r bind split means list. Split means looks like now a data table that tells us for every epoch and for every number of splits, what is the mean validation loss? And so if we do the same analysis as last time, you know, for every value of n splits, we compute what the min is. Let's take a look at the min. You know, the min number of epochs for the first split looks like it's 71, which gets the best validation loss. You know, and then after that, it starts converging towards, I don't know, here it looks around 61, here 51. Anyway, so now we can do our same analysis as last time. Let's take a look. You know, here we have for every different number of splits from 1 to 20, what are the corresponding mean validation loss curves look like? And here we have the minimum, the number of epochs which minimizes the validation error highlighted, sorry, the validation loss. So that's what it looks like to do it just for one split, right? So, that's one train test split, right? And so after we do that, we're going to run this code, and that's going to fit the whole model on fit the model to the whole training data set. And then here we have a join on, you know, for every, you know, number of splits, we know what the corresponding number of epochs which was selected was. And here, the validation accuracy, this is actually test accuracy. So that's hovering around 92%, just like we saw in the last tutorial. But so like I said, what if we wanted to do that for several different train test splits? So let's try to do that. Now, you know, so if we wanted to do that, what we'd have to do, we have to back up and put all of this code that we've written so far in a for loop. Right, so that's going all the way back up to the place where we started the model training. All right, so here we have actually all the way back up to the place where we started doing the train test split, right? So here we define test fold equals 1, but here let's change this now for test fold in 1 to n folds, where here n folds is 5. So what are we going to do? So we're going to execute all of this code every time, right? So computing a new train test split. Here we can move this feature plan outside. You don't need to do that again. But here, all of this stuff is going to be in the for loop now. And And what are we going to do at the very end of the for loop? So we have some data table maybe called test error test error list. How about that? So test error list, you know, is going to be a data table, or is a list of data tables with test fold and then this test metrics for all of the actually maybe we could do say that to a separate variable. Let's call that fold error and so here it's what we're doing is let's say we save fold error, and here we select the columns that we want to save. How about epoch and splits? Yeah, so for this test fold and for a given number of them splits, you know, the best epoch was epoch, right? And then let's see, the test accuracy was val accuracy. Let's see if that works. So if we run that, test error list not found. Okay, let's evaluate that to get that first. Test error list. So then this test error list thing, what is it going to look like? It's going to look like a list of these kind of data tables, where here this is for test fold 1 and for all the different numbers of splits that we tried. Here's the corresponding best epochs that was selected, and here's the corresponding accuracy on the test set. So what if we did that for all of the different test folds, right? So let's try to do that. Here I'm going to re-execute this whole big block. Here I'm going to put a print test fold at the top so we can kind of monitor the progress. And let's see what happens. End fold's not found. Yeah, let's execute that. All right, so maybe, yeah, so maybe it's doing the computation in parallel again, so it's not going to be super long, but we're going to have to do a little bit of waiting. So, what can we do while we're waiting for all of those 5 test folds to compute? What we can do is we can think about making the plot to show those test fold results, test error results. So first of all, this test error list. Let's go back up to where we can see that. So that's pretty much what we're going to be plotting. So let's call that test error gets do call rbind test error list, and so that's going to be a data table that looks pretty much like this. And so what we can do is we can just visualize that with a geom point. Right, so that'll make us a dot plot. On the x-axis, let's put the test accuracy values. On the y-axis, let's put the number of splits, because that's kind of the, the model parameter, right? So we're trying to compare what is, the best number of splits to do when we do our internal cross-validation. And then after that, we have to specify data equals test error. Kind of a misnomer because actually we stored the test accuracy here. But yeah, I mean that should give us a visualization of all of the five test accuracy measurements for each value of the number of splits. So looks like the computation is still running. Have we? Oh, something's happening. Yeah, it looks like it's maybe gone through a couple of iterations because you see it's going down, going back up now. I put in this print test fold thing, but I don't see any printout of test fold number. That's funny. hope it's actually working. Yeah, okay, yeah, so here it is. Here we have test fold 1, test fold 2, test fold 3. So we're on test fold 3 now, and we're waiting for that to complete. So, while we wait, is there any other optimization that we could be doing to the code? Well, you know, like we saw earlier, we changed a for loop to a future apply to do parallelization. You might think about doing the same thing here to this for loop, but since our processors are mostly maxed out most of the time, except for this little gap here, I don't think it's going to give too much speed improvements. So it's kind of important to look at your CPU usage if you're doing this kind of optimization, because if you're already maxed out, there's no point in maximizing your code or optimizing your code. At least not in, you know, if there's different kinds of optimizations, but in this case, there's no sense in putting in another parallelization instead of this for loop, because anyways we're already maxing out processors with this second level of parallelization over here. So it seems like it's working. Running the fourth one. Maybe just wait a few more minutes to see what the result looks like. I guess this means the fourth one is almost done. I guess the fifth one must be starting now. Fifth test fold. Yeah. So what happens, I think, is that, in this internal for loop, where is it? For well, so yeah, it's not a for loop. In this internal parallelization over the different splits, I guess it's throwing 12 splits onto the 12 different processors right away, and then after that, maybe, once those 12 are done, it's launching a few more, and then at the end it looks like it's not doing a full CPU utilization, and that's why we see that dip in the CPU curve here. So that means it's probably almost done. So let's scroll down and see what it says. All right, so here we got the command prompt again. And so here, let's take a look at what a plot looks like. So here, these are what the test accuracy numbers look like in the 5 different cross-validation splits. So you can't really tell which one is which, so you might want to add something like color equals test fold, or color equals, let's look at that first. It's not super informative, so you might want to change test fold into a categorical variable for different kind of coloring using this factor function. Yeah, then you can see all test fold number 4. Another way that you could do it is even just change this to a geom text where you have label equals test fold, right? And so here what you see is, it's for test fold 4, you have numbers which are hovering around like 90% for all the different numbers of splits, actually. So the bottom of the plot here, this is one split. The different test fold numbers for only doing one split for choosing the number of epochs. Here, this is for 2 splits, 3 splits going all the way up to 20 splits. And what we see actually is that for these particular data, there is a certain amount of variation, between about 90% and 94% for the test error numbers. but it looks like there's not a strong increase or decrease of test accuracy as we're increasing the number of splits. So actually what this says in these data is that doing one split is just as good as doing 20 splits. So you can just do one split and save some time. And so thanks for listening, and that concludes this tutorial.